Hi, in this part, we will be looking at further considerations about the missing data mechanisms. In particular, we'll be looking at testing or checking for missing completely at random and also how to prevent missing not at random. And I promise that it's the last video only about concepts. Starting off the next video, we will get more practical. But okay, let us start. As we have seen, missing completely at random is the only missing data mechanism that we can partially verify from our observed data. And in this direction, several statistical tests have been proposed to check whether the missing data mechanism is consistent with the missing completely at random assumption. And I should point out that these tests are not very often used in practice, and also that their practical value is somehow unclear, because as we have already talked about, we can never rule out missing not at random. What we try to do is to rule out missing at random. And I think it is a general agreement that maybe the practical value of this test is not to guarantee that data are missing completely at random, something that no one can guarantee, but possibly to, when trying to rule out that data are missing at random, to identify variables that might be correlated with missingness, so that we can adjust for in our missing data model, we can include them in our missing data model, or possibly when collecting data or designing further studies, we can also monitor or collect data about such variables. And Anders, the author of the book Applied Missing Data Analysis, one of the books from the reading list, contains a good discussion of these topics. Although what we will be seeing here, it's enough. So let us start with the most popular and simplest approach. And we have already touched this approach in a light way. So imagine that we have several variables, and for simplicity, that one of the variables has missing values. We know that missing completely at random implies that the missingness is completely unrelated to what we not observe, to the missing values themselves, and also to what we observe. And what we will try to check is on the variables that we observed and that don't have missing data, we stratify by missingness on the variable that has missing values. So I create, for each variable that is observed, I create two groups. One group that corresponds to those who have observed values in the variable that has missing values, and one group that corresponds to those that have missing values on the variable that is missing. And if I assume data, or if data are missing completely at random, the distributions of these two groups, or on average, they should be similar, because if they are not, it means that the probability of missingness is correlated, or the variable with missing values is correlated with this variable. So what we want to check is for all the variables whether these two groups are similar or not. And one way to do that is through a battery of t-tests. For each variable, we form the two groups, and we do a t-test with the null hypothesis that the means of both groups are similar. And we should be aware that the general conditions for the t-test to be used also need to hold here. And if we have a non-significant t-test, that is, if we do not reject the null hypothesis that the means of the two groups are equal, this provides evidence that the data can be MCAR, in the sense that we cannot rule out missing not at random, but at least we can rule out missing at random. And if we have a bunch of variables, in order for the data to comply with the missing completely at random assumption, we need to have a non-significant t-test. We should not reject the equality of means for all the variables. If for one of them we reject, so the data will be not missing completely at random. As I just said in the previous slide, possibly the main practical advantage of doing this approach is to identify auxiliary it's the way they are called in the literature, variables that we can later adjust for in the missing data handling procedure, or possibly when conducting further studies to be sure that that variable is included and measured. And this is the simplest approach. I personally prefer, rather than doing a battery of t-tests, I personally prefer using density plots or box plots. So again, for each observed variable, I construct the two groups, the group corresponding to those who have observed values in the variable that has missing values, and those who have uh, missing values in the variable that has missing data, and I construct the two groups, and then I look at the box plots or the density plots. So rather than just looking at the mean, I look at the whole distribution, and of course I need to do that for all variables. And as we can imagine, when the number of variables gets large doing the t-tests or looking at the plots, what I call like the visual checks, it can get cumbersome or even tedious, right? If we have like 10 variables we need to construct, and one variable with missing data, for all the other 9 variables I need to compute t-tests, I need to form the groups, and I need to compute the t-test, or I need to look at the distributions. And in order to somehow avoid these, Little in 1988, proposed a multivariate version of the t-test that can simultaneously evaluate mean differences on every variable in our data set. So rather than doing it variable by variable, Little procedure does it globally, and it's a check for missing completely at random that applies to the entire data set. We will be not looking at it, I leave the reference. And also there is this package. The package is no longer, it's still on CRAN, but you need to look for an older version of the package. If you try to install it directly, it will not show up, but it contains this function Little mcar that implements Little tests, in case you are curious and want to find out more. As I've said, I think, or it is generally agreed, that the main goal of doing the battery of t-tests is try to identify variables that might be correlated with the variable that has missing data, so we can later adjust for in our missing data model. And with the Little global test, because it's a global test, we lose this ability, because if the data are not mcar, if we conclude that the data are not mcar, we cannot identify what was the variable, if there is only one or several of them, what is the main force, let's say, driving the rejection of the assumption that data are missing completely at random. So I think Little test for mcar, it's possible not that useful, because as I said, as any test for mcar, we cannot rule out mnar, and further it does not allow us to identify individual variables that might be correlated with missingness. And now let's move to a somehow related topic, is that how can we prevent mnar missingness? And as we have seen last week, we had a quotation that says that the ideal solution to the missing data problem would be not to have any missing data, and that missing data prevention requires a careful experiments design and a careful execution as well. And most or all the methods, better stated, that we will see in this course, they assume that data are missing at random. However, we can never be sure that data are missing at random. As we have seen, we cannot verify this assumption from the data that we observed, and so we cannot rule out whether the missingness really depends on unmeasured variables or on the missing data themselves, but it's an assumption that we need to make and live with it. So when the study is being designed, a good idea is to start with a strategy that will somehow try or we can never be sure, but we will try to turn what could be MNAR missingness into MAR missingness. And this is called inclusive analysis. And basically what we try to do is to include variables that are known to be correlated with the missing prone variables. And so if we include such variables, we are more likely to satisfy the missing at random assumption, right? Because if we do not include such variables, and if missingness depends on such variable, we will fall in the situation where missingness is related to a variable that we do not measure at all in our data set. So it would be MNAR, but if we include such variable, then we could turn missing data, the missing data can be said to be missing at random. These variables are called in the literature auxiliary variables. And not only we should include these variables, but then in our missing data handling procedure, in our missing data model, we also need to adjust for these variables, right? Just including the variables in the data set, measure them, having them in our data set, but then not including them in our missing data model. If we have them in the data set, if the variable that has missing values is correlated with this variable, we have the variable in the data set, but we do not include the variable in our model, so missing data will be MNAR as well. It's not because we have the variable in data set, we have the variable in the data set, and we can use this information in our missing data model. Remember from the last video, when we condition on the observed variables, we need to make sure that all variables that are correlated with missingness are included in our missing data model. Okay, not including them in the data set, or collecting them, it's the first step, obviously, but then we need to go further and include the variable in our model as well. It might seem obvious, but sometimes it is not that obvious. And again, maybe we are not that interested in the auxiliary variables per se. Maybe they are not very interesting to our analysis. Maybe we are not interested in the relationship between these variables and our outcome of interest. But if they happen that they somehow affect or correlate with the variable that has missing values, we should include them in our missing data model, even if we are not that interested in the variables themselves. And how do we identify such variables? Well, with interactions with the experts in the field, and also, as we have just seen, by exploratory analysis using MCAR t-tests or some visualization checks like the density plots or the box plots. We will be looking at this in one of the videos for these weeks. And okay, we must be aware that including as many auxiliary variables as we can per se, we will not guarantee that the missing at random assumption is verified, but certainly it will improve the chance that it will be verified. For instance, I think this is an example from a paper from Andrew Gellman. It may be a strong assumption that non-response to an income question in a survey depends only on the gender, the race, and the education of the individuals, but this is certainly a lot more plausible than assuming that the probability of non-response to income in the survey is a constant, so missing completely at random, or it's only related to one of these variables, or related to gender, to race, or to education. So the more variables we try to include, the higher the chances that the missing at random assumption is at least plausible. And another way to avoid missing not at random is, or to try to fall at missing completely at random, or the missing at random cases, are the so-called planned missing data designs. And we have seen such an example on week 1, so last week, where we had the example of the nutrition study, and we were interested in the long-term fat intake, but this is time consuming and expensive. And so we had an example that a study was designed in such a way that for all individuals in our sample, they will provide their 20-hour food intake, and then only some subjects in the sample we would provide the longer fat intake diary. And depending on how such individuals are chosen, in this case, the missing data will be missing completely at random. In case those providing the long-term fat intake are just randomly selected from the sample of individuals that we have, or if they are selected based on some characteristics that are known and adjusted for in the analysis, missing data would be missing at random. And I have two examples here. One is a kind of extreme, but it's very common. So imagine that in a randomized study with two treatments, and we can think of the treatments of being a negative treatment against a placebo. We basically, the way the randomized experiments are conducted is we have the individuals that are enrolled in the study, and then in a random way we assign them or to the active treatment or to the placebo group, and then we measure the outcome of interest, the response to a treatment. And hypothetical, each individual in the sample has an outcome for each of the treatments. But since we assign subjects to only one of the treatments, the outcome for the other treatment is missing. And it's missing in a completely at random fashion because the subjects were assigned in a random way to one of the treatments. It might seem a very extreme example, but in fact, treating randomized experiments or randomized studies as a missing data problem is very common in the statistical literature. And in fact, this example is one of the simplest examples if we want to think about causal inference and the the hypothetical outcome that is not measured because the individual is not assigned to that treatment is known as the potential outcome in the causal inference literature, something that it's a hot topic by these days in the statistics community, and that, by the way, was also started by Donald Rubin. And this is an example of a planned missing data design where missing is completely at random, and another example of planned missing data designs where in this case missing is at random. For instance, imagine that is the case where the selection designs where values on one variable determine whether the individuals will provide data on a second variable. And for instance, imagine the case where we are looking at the marks for first year university students, and it's often the case that the universities use some exam marks to control the admissions of students at the university, or a combination of high school marks and exam marks, but somehow you need to score above a certain threshold in order to be admitted to the university. And so those who are not admitted to the university because their score was below the threshold, they then would not provide a response to the second variable if the second variable is the first year marks at the universities, right? So we have two variables. The first variable is the high school mark in combination with the exam mark or whatever it might be used by the university to determine the access to studies. And then the second variable is the first year exam marks, the average, for instance. And so we only observe the average of the first year exam marks for those who scored above the threshold. So missing in this case is at random. And there are several examples in our classic example of the BMI and glucose levels. For instance, we could think that only those with very high glucose levels, for instance, would have their BMI measured. And in this case, missing would be at random, because for those with glucose levels that are not very high or not above a certain threshold, we would decide not to measure their BMI. So we know the reason for why we have missing data. This is an hypothetical example, but it's again an example of a planned missing data design. And yes, that is everything in terms of concepts. In the next video, we will be a little more practical and see how R handles missing values and look at some practical examples. So see you in the next video. Thank you.